In this first talk, I will talk about the present status of the GPD extraction from the DVCS data. So I will make a short introduction. I see only experts here, and who is looking online. So there are also some experts. So I think there is no need to really go really deep into this introduction and explain what are GPDs. But I will do some short introduction to set the stage. I will show you the present status of the fits to the DVCS data and some new developments there. But most of the time, I intend to focus on actually what can we learn from the fits. So you will, I mean, the final goal is obviously to learn how the hadron is structured and what can we know about GPDs and Compton form factors. And obviously, this will have to do with the present uncertainties of what's coming out of the fits, so uncertainties of structure functions. And then I will argue that neural networks offer really a nice tool to assess the uncertainties of the structure functions as known today. So just to remind you, on DVCS, it's a process where you probe hadron. In our case, it will be proton all the time with a virtual photon and produce a real photon, and this process interferes because you measure it in lepton production, it interferes with the beta hyperscattering, and this interference obviously gives you access to the real and imaginary part of the amplitude. So to remind you on the cross-section because of this interference has three terms: beta hyper squared, DVCS squared, and the interference term. And each of these terms can be expanded in the short Fourier series, where in terms of the angle between lepton plane and the photon hadron plane, and the coefficients in this expansion are then expressed in terms of Compton form, so-called Compton form factors, and known as elastic form factors. So for the purposes of this talk, and this is also some sort in some state of the art in the DVCS fitting, we will stick to really leading order Compton form factors, which are these four guys here: H, H tilde, E, and E tilde. So I will discuss a bit later whether we at this point need to go beyond that, but let's stick at the beginning of this, stick to this four. So as you know, the Compton form factors factorize into the convolution of the known perturbative coefficient function and the GPD, which is like the final goal that we are aiming for. However, I will not really, I will also mostly stick to the extraction of the Compton form factors, because this is like the first step that we are trying to do, and obviously good knowledge of form factors will then be, we hope, you can translate it into the knowledge of GPDs. And also Compton form factors have this advantage that they depend on one variable, one kinematic variable less, which turns out to be very important in this data fitting and instructions and the ZEUS. So the model that we use over the years, this is a collaboration with Dieter Müller. It is a hybrid model where you describe seq-works in a conformal moment space. I will not describe this in detail. And it turns out we use XL3 partial wave expansion. We use proper Q-square evolution. And this is how we describe seq-works in gluons. This is especially important for fits to the HERA collider data, where they are sensitive to these partons. And the valence quarks we model actually directly Compton form factor by the GPD-inspired ansatz, which is written here. So there is this, you can recognize the ansatz, which is quite similar to the ansatz used by the PDF fitting people. So you have some x to the alpha minus alpha Reggie controlled small x behavior, then you have large x behavior controlled by this parameter B. Momentum transfer dependence is controlled by this alpha prime parameter here in the Reggie trajectory, and also there is a residual dependence here. So you have this mass here parameter, this B parameter, Reggie trajectory is fixed, and there is a normalization parameter R. So about 3 parameters per GPD. This gives you the GPD. And this so-called crossover trajectory gives you imaginary part of your Compton form factor, and then the real part is determined by dispersion relation. So in case you have subtraction constant, as you have for agent E, Then we also parameterize this subtraction constant by 1 or 2 parameters. And so in total, we have like, in this model, you will have like 15 parameters in total, right? So, and this model is then fitted to the data, and you have, at this point, maybe, well, depending on how you count, you can have several thousand of data points coming from HERA, Collider, from Hermes, and from JLab, and now from Compass. And however, we fit mostly to the Fourier transformed data when data is measured over phi. So we use in practice like 300 of data points in our fits. And I will not now, since probably there is, yes?
This H, is this a combination of U, D, and C?
Yes.
Yeah. There's no flavor separation.
Yeah. No flavor separation here. This is only flavor separation will be enabled by meson production or by neutron DVCS, but I will not go into that. So we are flavor insensitive here. So, I will not now really show you how the fit work throughout the all available data. I will show just plots for illustration from the 2 opposite ranges of the XBjorken. So for HERA, this H1 and ZEUS data, you can see that you can fit quite nicely T dependence of the DVCS cross-section, then W dependence, Q-square dependence is here, quite nice. So there is no problem here. And also you can go on the other opposite end of the XBjorken span and consider JLab whole A, which is XBjorken 0.36, and you can see that fits reasonably described data. This is, for example, this is a total cross-section, very, very precisely measured as the whole A and very nicely described. This is the cosine phi dependence. There are some slight discrepancies here, but really nothing to be worried about. So the global fit at 2015 was very nice and fine, and in some sense, you could say it is possible to describe data with this model that we use. I will also show you here now chi-square values, and I will compare the results from this fit I do with Dieter-Müller with new. There is a new group. This is all group, but there is new results from this group, France-Polish group, Bukart, Snyder, and Wagner. They work within this new PARTONS framework, and they also have this year published new global fits. So these are the new global fits. I'm just mentioning them. There is nobody from this group here, so I will compare this. So just you can look probably just this. I'm not sure if you can see it. These are Q-square values per degree of freedom. So you can see that they are around 1. They are now written here in terms of which experiment that we use. So this is Hermes, ZEUS, CLAS, Coley, and so forth. And you can see that this KM15, the most recent model, is really describing everything nicely. There are certain problems with longitudinally polarized data, target data, but it's really mostly due to 1 or 2 outlier points. So I would not consider this a true problem. So description is nice. And also, the PARTONS group have similar results. They have some problems with this compass, newest D slope point. I will not go into that, but also they mostly describe data nicely. The difference between us is that we use also this collider data, ZEUS and H1, so there's no data here. And we also include whole A total cross-section. They work mostly with whole A cross-section difference between 2 beam polarizations. So this cross-section difference is somewhat easier to describe, and whole A total cross-section, which is the most precise measurement in this world fit, has always been some sort of a problem for the fits. You know, already starting from 2006, we had problems with this data. Then this measurement was superseded by the newest version, this 2015 measurement, and then it somehow fitted nicely, right? But it is, for example, there is a new measurement now, last year's measurement, and actually including this last year's whole A measurement to the global fit results in, I must admit, a failure. This is very precise measurement on several beam energies. So in principle, it offers us some sort of a Rosenbuch separation of various form factors. So it would be nice to really be able to describe it. Presently, a simple application of our model to this data results in a problem, so to speak. So I would say before this data, we have nice fit. After this, we have problems. This might, I mean, educated guess would be that this probably points to the necessity of introducing higher twist contributions to this model that we are using for fits. And this already by Vodoja and his collaborators somehow calculated, and we have it at our disposal. So it's a matter of manpower to really introduce it and to see whether then the data will be fitted properly.
We had no higher twists in the previous video.
There is no higher twist effect. So it's just leading twist for component form factors, the most simple approach. So this most simple approach is enough to fit essentially everything but this data. There is some controversy about this 2015 data. As you may be aware, the whole eight people have a claim that even this 2015 data require higher twists. In our case, we somehow disagree, but this is somehow technical point. Here we somehow truly have a problem.
Just one comment
Yes.
and a question. We'll have a discussion this afternoon. Volodya really give a short summary about higher twist.
Okay, excellent.
In DVCS. But I want to ask, in this kinematics that we're referring to, do you or Volodya have a rough idea of the size of higher twist corrections? It will be 10%, 30%?
Yeah. It depends on, I mean, okay, higher twist, you have kinematic higher twist, you can have genuine higher twist, which you cannot really assess.
I mean,
all large. But for kinematic higher twist, certainly effects of, as you say, 10% are easily there, and you can do more. And you can, depending on the observable, of course. I mean, this cross section is very precisely measured, so. Yeah, you can certainly, I mean, I would say that including those higher twists, especially if you parameterize them somehow, for example, if I can introduce higher twist GPDs as a separate parameters in our fit, and then fit this to the data, probably then the fit would work. But then you can...
I think that's correct, that this generically, for generic observable, it's like twist for corrections are like 10% effects.
Yeah.
And genome is, I think, will be much less.
Yes,
But there are these 3 months of Vilchik, which in certain regions of kinematical space can be 100% effect. And that is
so it's really
this is just there. Yeah,
it's dynamically twist too. It's just
okay. This is also not included here, but this can be 100% at some observables.
So it's probably something to discuss. And I mean, you can see from this, I mean, if you take just this data, it can be fitted. I mean, just 2017 data.
so the blue curve is only
2017. Blue curve is only 2017, and you can fit it. Okay, I mean, you can consider this a discrepancy, but it's, I mean, statistically, it's not a problem. So you can fit it with just this 2017 data. However, in the global fit, which is the red curve, which is the red prediction, then you are wrong. If you want to just take global data, including 2017, you cannot. However, I must admit, due to the lack of manpower, it was not really, you know, I mean, we just did somehow just try to fit it, just ran those scripts and see what comes out. And this comes out probably maybe some careful considerations and maybe small adjustments to the model could result in a better fit. But let's I'm not sure. I honestly, I cannot say. And at this point, the situation is like this, considering this newest data. And obviously, even better data is coming from this JLab 12, and so we have to be prepared for that, and we have to really probably improve our model. Yeah. But okay, somehow the subject of my talk today is maybe not so much. Okay, but this is obviously of paramount interest to understand whether we can fit or not fit the data. But somehow I have aimed to make this talk more about assuming we can fit data. What can we learn at this point, right? So let's do that. So obviously, what we need to know is if we, for example, now disregard this 2017 problem, consider the data that we fitted successfully, and ask yourselves whether you can now, what can you learn from these fits, and how the GPDs, or at least content form factors, look like coming out from these fits, and what are the uncertainties. This is really a problem in the sense that throughout the years we have never published the error bars. We were always asked, what about error bars? And we never published them. We were reluctant to publish them because there are always uncertainties that are not under control, right? But obviously we have to address this question, and for example, people are asking to assess the impact of the EIC on this learning of the form factors and GPDs. What can we learn if we increase energy, if we increase luminosity, statistics, and so forth? How can we zero in on the structure, on the distributions of gluons or whatever? So in order to answer these questions, you really want to have some error bars, and you see, okay, now I go to EIC, these error bars go like this. And we did that with Salvatore and Elke at some point for DVCS data, but this is really very much model-dependent analysis at this point. And so this is the question that one should address, and I will address this question first in the simpler setting, and I will try to answer the question how uncertain we are about the value of the D term itself. Not only because D term is discovered by our convener and Max and Polyakov together, but also because it is really interesting object, because it is somehow has a nice physical interpretation, which has now come into the focus again. We often use it we sometimes we often use this G-sum rule and tomography Matthias to explain the physical content of our studies to people outside of our field. And now I think we have this third thing, which was always there, but was now really coming into the focus, really a D term, which has this nice physical interpretation related to the pressure distribution inside the nucleon, but we will have talked tomorrow by Peter Schweitzer about it, so I'll not go into that. Within some approximations and after some charge-related prefactor, the D term is closely related, essentially maybe even equal to up to very small difference of 20% to the subtraction constant in this DVCS form factor. So you can express it as a difference between the dispersion integral of imaginary content form factor H and the real H. So if you can measure these guys, you really can get to these D terms. So the question is, how uncertain are we about this? Because obviously we use imaginary H and real H in our fits. So can we have say something about D term? Actually, in our fits, a subtraction constant is directly modeled. So what we get out of our fits is exactly the value, essentially, D term. And here are the results over the years of different fits. So you see, it's really, this is minus D, so it's positive. It's all over the place, as you can see here. And it is good to compare this. This is the plot by Peter Schweitzer and Max Polyakov from the recent review. We gathered the values of D term from various studies, both theoretical and this experimental study I will now discuss as well. And okay, signs are roughly agreeing, but values are all over the place. And it is, in some sense, we argued that why is this all over the place? It's not because the data changed over the years. These are the change over the years of our model, but because data haven't changed that much, but because we use slightly different models, and a real part of the DVCS amplitude is not so sensitive to experimental data, or the other way around. So in some sense, we thought that this is mostly the measurement of the systematic knowledge, of systematic error coming from not good knowledge of the model, right? We have, so yeah, if you just propagate the experimental error to these fits, you'll get error about 20%. But there is a systematic uncertainty due to the model selection. It's presumably quite larger. It's of the order of like how much these curves are spread. So, and then you can compare this to this very interesting, very famous new work by Volker, François Gillot, and Latifa. They used just class data on cross-section and cross-section difference to really extract D term very precisely. You see this really the smallest error bars here. They should be multiplied by maybe 1.5 because systematics are not so statistical, but they are still extremely precise. So this would mean extremely precise knowledge of pressure inside the nucleon, and it degrades things. So there is, in some sense, there is a disagreement with this, and we try to address and to understand this, because, as said, this error comes mostly from the experiment, and obviously we don't know how much error comes from the theory and from the choice of the model. They used also the parameterization similar to what we use, so it should be comparable, right? It's not apples and oranges. And to assess this systematic error coming from the model selection, we can maybe learn something from the people coming from the data analysis, which is a huge scientific field that has really a lot of knowledge about this influence on your uncertainties coming from the selection of the model. So in the language of data science, total error of your prediction is separated usually into the bias and variance. So variance is what is coming, the error coming due to the imperfections in your data. So something that you will probably call statistical error. And bias is what you will maybe call systematic error. It's coming from the lack of the ability of your model to describe the true structure function, right? So this bias is really what we are after here, because we would like to know how much problem is coming due to the model selection and how much. This is my thing. Yeah. Okay, so this bias is really tricky, and obviously we cannot calculate it quantitatively because we don't know the true structure functions. Bias is like a difference between what your model can describe and the true structure function. And since you cannot, you don't know true structure function, you cannot quantify it. But what you can do.
The dispersion of those curves, for example, is not like an estimation of the bias.
Yeah,
because you change the model.
Yeah, it could be, but it's just like an hand waving estimation, right?
Yes.
It's a bit more complicated than that. And but now, if you want to really estimate the bias, maybe you should go to this some sort of a toy model where you know the true structure function. I have this because one thing that is important to notice is that error can shift from the bias to variance, right? If you have a very rigid model, then also, which is known from these studies, is that your error will also, statistical error will also decrease, right? Because you have larger error in your bias, then the variance will be smaller. So you can be somehow fooled that you have really small error bars, but this is only because your model is too rigid. And there is this really simple toy model. I don't have time to really go into details, where you take some sine function, which is really like a known structure function. You measure it at 2 points, and then you fit it with two different models. One is flexible 2-parameter model, one is rigid 1-parameter model, and you do some analysis, which I'm not going to explain in detail. You can do with this guy and this here, and there's a YouTube lecture about it. And the end result is, if you have a rigid model, this gray area is telling you about the variance, the resulting statistical error. And rigid model will result in much smaller statistical error in the flexible model. So you can be fooled in some sense by using very rigid model to get very smaller. I mean, in the limit, you can just take a model. Your function is equal to 1 or to 0, very simple, and no error will be 0. So you can understand this limit. But obviously, you can be more quantitative if you want. So people in data science often deliberately use rigid models if they have few data points in order to decrease the total error. Because as you can, if you study this closely, you will see that actually this rigid model is better. But in DVCS, the situation is opposite. We have a reasonable amount of data points. So we would like to have a flexible model so that we decrease the bias and that the error bars coming out of it can be considered realistic, right? So this is what we do. And this is why we try to use neural networks, which are mathematically proven to be unbiased functions, which can really then work unbiased. And then what error they give you is essentially total error. So this is some advantage, and this is why neural networks are a good tool in this science. So I will show you now, the neural networks that we use. They model content form factors, separate imaginary and real part. Sometimes only imaginary part and real part is extracted by dispersion relations. Then we have to model subtraction constant by neural network as well. And this is essentially just least square fit to very complicated many parameter function where these neural connections are some weights which can be fitted in order that these content form factors match the data. So without explaining this in detail, I'll show you results of 2 studies. One will be neural network fit to just this CLAS 2015 data, so that errors can be easily compared, for example, to this study by CLAS people published recently in Nature. So we fit the CLAS cross-section and cross-section difference, and we use also just the one simple conform form factor. So it's a very rigid model, so to speak, just one conform form factor H, which turns out to be enough to describe just this data, and this is what they did as well. We will utilize dispersion relations. Uncertainty is estimated by just averaging over ensemble of the neural nets. We fit ensemble of neural nets, many of them, and these are for example, this is how it works. Each of these lines is one result, one good fit to the data, right, given by the neural net. Both, as you see, you can have reasonably different structure functions. This is imaginary age, this is real age, and they both fit data nicely. In these plots, you will always have 2 cones. One cone is where the x-axis is just restricted to this CLAS kinematics and up to Hermes, while on this other plot there is a gray area which is equal to this x-axis on the left-hand side. However, there is also extrapolation all the way to the x0 and all the way to the very small x of 1. So that you can see the effects of extrapolation of these neural network results, which is needed when you do this dispersion integral. You essentially integrate over all x, right? So, and this now, when you average over these nets, you get these error bars here, right? So these are the results, and you can actually plot these results together with the results from this study, which is very precisely termed, but we'll get it all. And okay, now you can see there's reasonable agreement. There is not complete agreement with imaginary age. Real age, well, there's a shift here which has to be understood. Maybe some technical differences, I don't know. But I'm not going now to discuss this central mean value differences, but mostly about errors. These errors are what I'm interested in. You can see, for example, another thing here, that a real part of age coming from the global fit in this model fit KM15 is quite different here. And it still describes the same data well. And also you have a very famous Gauss-Cockcroft model. Here, you see, it's completely different. Well, it describes this data just slightly worse. It's a prediction, not a fit. So you see, these are the chi-squares of Gauss-Cockcroft. This is the old KM15 fit. This is the neural network fit. So all these guys describe data well. So you can see that there is a huge span of values of real age, which is good enough to describe this data. So the effect really, it's really difficult to know. And the term is somehow difference between this and integral.
Does this incorporate the dispersion relation?
Yes. Okay. Well, yeah. All these guys incorporate dispersion relation. Yes.
So the real part is computed from the dispersion relation from the diagonal. It's not computed through the convolution integral.
No. Real part is computed as an integral of this imaginary part, extrapolated to 0 and to the small values, and minus dispersion or plus, depending on the subtraction constant, which is separately parameterized by neural networks, right? Okay, so if you now, and if you use more flexible model, for example, you add H tilde to your model, you will see what happens here. So the blue model is the old one, and the green model is now including H tilde, so you have new contributions from H tilde. This is the tildes here. This is imaginary H tilde, real H tilde. And you see that imaginary H shifts significantly due to introduction of the new part in your model, right? Real H as well is changing, right? So really, and then resulting, this purple here are the same as here. So the resulting control form factors are, for example, more agreeing with this Burkett study, real also, maybe. But the point is that when you go to more flexible model, things change a bit, right? So you can add also more data points, and you will have, for example, adding Hermes beam spin asymmetry, and the model now includes also E and H. Again, imaginary H shifts significantly, of course, and you see extrapolation here, so integrals will be different, and so forth. The final somehow point that I'm trying to make is that if you now calculate D term out of this neural network fits, you have two results here. The error bars will be huge because of this uncertainty in extracting the real part of your age. The error bars will be quite huge. They are consistent with the, I mean, the D term is consistent with the D term coming from this study by Kumericki et al., also coming from our recent study 2015 global fit. However, the error bars are much larger. So my claim at this point is that if you take just plus 15 data alone, it is still consistent with zero D term, right? And for example, this is just okay. This is the result of the fit plotted back on the data point, so you can see the error in the fits. So the small error here is just a result, and from the huge, I mean, huge, not huge, but a really large D term error and relatively large compound form factor error, resulting cross sections are really small error because the cross sections are not so sensitive to this D term and the real part of the compound form factors, right? So really, to get to the D term, probably we have to go to the I would say to more data. I mean, we have to include the global data. Just concentrating on this class data, I would say it's not that. So, okay, and by the way, there is an independent way to reach the same conclusion without neural, if you don't trust neural networks, which you may not, it's a bit convoluted procedure, and you cannot reproduce it easily without a lot of manpower. So you can use, there is a model we published in 2009, and you can just put subtraction constant to 0, which means D term 0, yes, and this model, which is an analytic model, simple function, you can take it from paper, it really describes the same data perfectly, right? So this model as well, which the D term 0, this also shows you that really out of this data, D term is really difficult to extract. You have, I mean, the point of the plot that we've published recently in this this plot here that I start, we actually published this plot in order to argue that to get to the D term, we probably have to have good data on beam charge symmetry or double DVCS on these observables which are more sensitive to the real part of the amplitude. Okay, so and just I have no more time. I already overstepped it. So just to show you also the result of study B. This is a neural network fit to the world fixed target data. There is a representative subset. This is not a complete set, but it covers. Doesn't cover HERA. Okay, it's fixed target, right? And it's Hermes data, also polarized target, class 4, everything is here. Not the 2017 data, I must admit, which is problematic. And we will now use completely unconstrained neural nets representing all compound form factors without assuming dispersion relation. So it's a bit like a most flexible model that we can have. And we fit it to the world data. And what turns out, what we can consistently extract as different from 0 are these three compound form factors: imaginary age tilde, and real E, right? And they are plotted here and extrapolated here. And with a somewhat smaller significance, you can also say you can reach real age and imaginary age. You can, depending on how you look at these plots, if you consider this some sort of extractional function or not. I mean, it's in principle consistent with 0, but there is something seen here. So I'm reading this to you. And these three guys are really consistently extracted. And so this is like the first plots of the compound form factors, which I believe have really error bars which are kind of realistic. And if you take other compound form factors, you include them, obviously they are included, and if you plot them out, they'll come out consistent with 0. So for example, imaginary age tilde coming from this neural network analysis comes like this. So you can fit the data regardless of the value of this. So you can probably put some bounds, but as you can see, these bounds are not very stringent. So not much can be said about this. So to conclude, I would say that the neural network method has really unique capabilities to address this question of the uncertainties, and we have to hope to use it more to really in the future to really maybe use it for assessing the impact of the future experiments. And I would say that this is the way to get the reliable uncertainties. Obviously, model fits that we also do have their place because they they have some. You can gain more physical insight from them, and we'll not obviously throw them away. We'll do that as well, but neural networks have really nice. And I can just advertise we are having some server, which is like a DARM server for PDFs, for GPD, okay, not GPDs, but content form factors, where you can get plots of the fits coming from this, not this newest neural network fits, but will be soon there. Also, numerical values will come during this month, so you can use it in your studies. Okay, so thank you for your attention. No, sorry, who is chairman? Okay,
I just wanted to say that, in my opinion, the P term, the value of the T term, will eventually come from the lab. So that's one contribution that is true. I'm very skeptical about extraction of the whole GPD, but the D term can be extracted with reasonable precision, and I think this will come relatively soon.
Yeah.
The time scale of this experiment that we're discussing, this will
what's the operator?
The operator is standard how we define the term. The problem is only you have to get the term which is proportional to the delta mu delta u, which means that you have the powers of momentum, but since we now have full control so we can really inject rather large momentum. I think this is something that this really can be done.
I mean, lattice has already done that, right? We already have a D term from the lattice. And
the question that to do a serious lattice calculation, it will take quite some time, and it will be expensive. But this is certainly possible. It is difficult to say to reach accuracy because it will depend on how big it is. If it is big, it will be good accuracy. If it is small, it will be worse accuracy. But for you, it's the absolute uncertainty is what.
Well, then we will use this lattice result as some sort of a benchmark for what we can.
I think so.
Do
I think that is really the point where lattice can give it.
Thank you.
It's just maybe not for the whole T dependence.
Peter?
Yeah, you mentioned that later you will extract GPDs from your form vectors. But do you not need additional information to make the flavor separation?
Of course, yeah. Okay, we can maybe. I mean, what we did, for example, when we did the HERA data, then we can just concentrate on, for example, singlet combination or gluon GPD, and that can be done to a certain extent. For the flavor separation, we would need some additional data. That's true. That is not possible with this DVCS alone. Yeah. So. We hope to include meson production also to the fits, and we started that. And there are some preliminary results by Tobias Lautenbacher and Eva Miller and Andreas Schäfer, which are now still unpublished, but there are some preliminary results on global fit, including DVCS and meson production using HERA data. It is not easy to fit, but they have been successful. Well, the model is a bit problematic, maybe, that they had to use in order to fit the data. So it's really a difficult task, but it will have to be done. I mean, the idea to have universal functions, which really are hadronic structure and not just some fitting function that describes your data. But if you want to really learn your hadronic structure, then you have to be able to describe both GPDs, both DVCS and meson production. But it's for the future.
So I have a question. So how unbiased is this neural network approach? Yeah. So for instance, do you have to tell it that there could be higher twists, or it will find it out by itself?
Yeah, okay. Depends on which. I mean, if you talk about genuine higher twist, then yes, you will have to tell it, and you will have to use separate neural network to parameterize it. Kinematic higher twist, it's just a matter of formulas for the cross section. In some sense, or Vanjura-Wilczek, you can just have it in the cross section and use the leading order twist coming from neural. But yeah, in principle, they could be as unbiased as you like it. For example, in the studies that we did, the only bias we introduced is that we force it to be zero at endpoint. Right. This is something that also people who do PDFs fit do. This is possible to do in an unbiased way, right? For example, you can say that introducing the dispersion relations and forcing them to obey dispersion relations is introducing a bias. But however, if you have some physics that you really trust, like dispersion relations, for example, you trust them, you can introduce that. it's a pity that some other good knowledge coming from physics is not so easily introduced into this neural network fits. For example, constraints coming from some rules like form factors, elastic form factors constraints, which GPDs has to obey. This is, I still don't know how to include this, and this is a pity. I would say this would make this method more powerful. So I would say, in principle, yeah, you can make it totally unbiased. That is easy, actually. This is what, I mean, the final results are totally unbiased. There is no assumptions whatsoever here. But it would be actually nice to be able to introduce some sensitive bias that would make it somehow more predictive.
I think there is a confusion because, of course, high at risk can be defined by linking this with this neural network.
Yeah.
The question about high at risk is not because you can fit the data without high at risk, so you cannot fit the data. And I think you will be able to fit the data without high at risk, but that's not the point. The point is that if you have extracted the part of the GPDs without high at risk, you extract the wrong part.
Yeah, that's
Yes,
okay.
so this is
yeah. That's true. That's true. I mean, high risks are there. You have to. If you know,
it's there.
Yeah, it's there. Yeah, I agree. I agree. I agree. But
normally, when you see neural network on PDF, they have very big uncertainty when they go outside the measuring region. In our case, we don't see this big uncertainty.
Well, we don't go that far as they do. I mean, their uncertainties really are, for example, for gluons and stuff, and when you go to 10 to the minus 4, 10 to the minus 5, my plots stop at 10 to the minus 2, for example, and they are sometimes influenced by Hermes data, which is slightly the lower X. So I would say that if I go further, that they will really, I mean, there were some early results which were plotted also to smaller X, and there were larger spread of this.
Because the small X will enter especially in the real part.
Yeah, that's true. But it is also true, we tried to assess the influence of the small X integral is not influencing that much the dispersion integral, because really it's just integral up to 0.01, 0.05 or something like that. And integral goes to all the way to 1. So, I mean, if you start, now the question is, for example, if you want to introduce Regge behavior, that if you trust it, then really the small X integral can be somewhat problematic. And then that would be an important question to ask when you don't go to really small X region with and introducing small X data. But now sticking to this valence part, yeah, I'm not sure this is really. I try to make some sensible attempts to guess how much error comes from this really small X, and it's not much.
Yeah, I'd like to follow up on that with a question, because that's actually an important topic for the electron-ion collider. To what extent are the analysis of large X GPDs and small X GPDs, to what extent are they independent, and to what extent are they related? I'm asking for the following reason. So the neat thing about DVCS is that we have dispersion relations for the moving twist amplitude. So they relate low and high energies for large X and small X. So is it, for the purpose of analyzing the HERA data, would it be enough to describe the large X part in some class action fashion, just in the sense of a few basic parameters, no details, and do kind of like a self-consistent or autonomous description of the HERA data? And or conversely, for the purpose of, say, describing the JLab data, is it do we need to know what do we need to actually know about small X? Is it enough to know a little bit about asymptotic behavior and estimate some tail in the dispersion integral? I think that's a very important question for the electron-ion collider. So is the direction more that of a real global analysis where we have like massive flow of information between large X and small X? Or is the direction more that we do kind of one type of analysis for large X with a summary description of small X, and another type of analysis for small X?
We definitely
that's very important, because also, in all honesty, the physics of the GPDs is also quite different in the valence core region from the small X region. So
No, I mean, we did definitely this second approach at one point. We fitted just HERA data just with gluon and C-quark GPDs. We had it separate in our model. And then this is fitted to HERA data and then just fixed, and then evolved to the large X of JLab, and then just use the valence part of the model to fix the JLab, and it worked. But it somehow it didn't seem right. So now we just have used the total model. So C-quarks are also adjusted to the HERA data as well. Although probably the influence of the fixed target data to the C-quarks and gluons is not that big as the influence of the HERA data, right? But you are right. I mean, it's a game where especially in this dispersion relation, where integral really gathers the information throughout the region, right? So yeah.
Yeah, that's a kind of more global discussion.
Yeah.
That's in the afternoon.
Okay.
Has anyone thought of, for example, using subtractive dispersion relations where you deliberately suppress the information from high energies that enters, or conversely, like finite energy samples where you wait with powers of the energy and emphasize only the high energy part?
Yeah.
There's all kinds of.
We tried to play with this. There is some paper with Dieter Müller about exactly that, like some sort of finite energy sum rules, where we try to like cut off the dispersion integral and see how much you can lump the information coming from a certain region, like large X or small x, into some constant or something, and then what you can do with that. But it was very like theoretical and not really applied to the real data. So it's a work to be done. Nobody has done something like that, but sure. I mean, we have some years now before ESC, so why don't we try that as well?
Is there anything known about the gluon term?
Gluon term. Oh, let me think. Right. No, I mean, it comes in our analysis. It comes all together. I mean, we have like we are not sensitive to particular flavors, and in the content profile we have just this so to speak subtraction constant, which somehow includes everything, right? And we cannot separate it. And I'm trying now to remember in these old models which we used just for HERA whether we had. But no, also there it was completely lumped together. So we cannot, in modeling, especially in the model independent way, we cannot really separate the gluons from the quarks here.
So now I'm confused because the term which is shown in the paper information, this is for the quark?
This is for the quarks, yeah. I mean, it's interpreted. I mean, it's experimental. It's an experimentally extracted as a subtraction relation, as a subtraction constant in the dispersion relations for the GPD age. In principle, it contains contributions for quarks and gluons, right? But it is somehow assumed that it's just quarks in some sense. So if you want to interpret it as a pressure of quarks, then it's just quarks, and somehow there is no discussion of this particular.
In higher orders, it becomes independent.
Yeah, it's and this level is just just D term. It's just subtraction constant, and it's somehow some flavor combination, which in principle includes gluons, but you cannot really tell.
We pointed to the relative lack of data on the real constraining the real part of the DVCS sample. So what could we do to improve that?
Okay.
And, what do we expect, for example, from the compass charge asymmetry?
Yeah. Okay.
Well,
their charge asymmetry is correlated with spin asymmetry. So, but yes, there is definitely something to be learned from that data. So we hope to get it soon. And the beam charge asymmetry from Hermes is having some doing some also constraining of this stuff as well. So actually, this last study, when you try to describe in the neural networks beam charge asymmetry and use dispersion relations, then some problems are creeping out. So I cannot say much about it. I'm still studying this. So beam charge asymmetry could be really important, right? So I somehow hope, I understand there is some initiative to also have positron beam at JLab, and that would be great, for example. Right? And then obviously double DVCS. This is, as I said, this was the plot that we did with this span of various D terms that was motivated by this conference about DVCS. So this was like, because DVCS is sensible to this central region of the GPD, when X is less than beta, right?
Staying within conventional DVCS, is there any way you see that at the EIC we could especially target the real part of the DVCS amplitude? Short of using, say, positron beams?
Yeah, short of that, I don't know. I don't see it immediately, but I must admit that I haven't thought about it. What can we see, tell about it? Somehow.
So, again, I'd like to remind everyone that we'll have a dedicated discussion about DVCS this afternoon. And if anyone has some idea for a larger topic that could be discussed, by all means, bring it up, and then we can make a kind of tentative structure and maybe have someone introduce that topic so that the discussion can be done more efficiently.
Okay.
If there are no further questions for Chris, let's thank Chris again and coffee break. And there are some special circumstances about the coffee breaks which are